question related to the midterm. Everybody knows and is aware of the time and the date of the midterm. Everybody is aware that we have to use responders. Everybody is aware that you cannot use Excel during the midterm. Now, concerning the midterm, yes, it's going to be multiple choice, around 20 questions, around 30, 40 minutes. I don't know yet. I need to solve it and time myself. And it's gonna be what chapters, Andrew? It's already in the announcement. It's chapter 1, 2, 3, and 5, along with chapter 0. You need to know all your data analysis. The error on the slope will not be given to you in terms of you need to do the calculations, but probably it will be given to you in such way that you have to pick between the different choices A, B, C, D. Okay, so you need to know, for example, how to round it, how to write a unit, but you will be given the choices. We will make sure not to waste your time by asking you to do your own calculations, you know, for the error on the slope only, because we know it's time consuming without Excel. So you need to know all your data analysis very well, the theoretical background for all the labs, and a lot of conceptual understanding. Like, for example, what happens to the period when you double the length and so on, you see? Like the conceptual behavior, the sketches, you know? And a lot of data analysis. You will see very simple and random questions about something that is measured through 5, 6 trials to find the average and the RMS. Okay? Yes. And if you remember any question related to the midterm, just simply send me an email, okay? Yeah, so midterm, I suppose you're done. Backtracking allowed, I think it is allowed. I don't know, actually, we did not decide upon this, but we're not gonna make it difficult for you, okay? I think it's gonna be allowed. You will know later, okay, Eli? I'm not confirming it yet because I did not think about it. But personally, I want it to be allowed, okay? Because I don't see why not. Any other question? Yes. So the point is not to put you in very difficult situation. The point is just to make sure you know how to do your minimum requirements of data analysis, error analysis, and conceptual understanding for us to move on. And we don't want you to be surprised in the final exam. So this is like a rehearsal for the final exam. And please don't waste your time studying a lot for the midterm. Khalas, you know those skills, apply them. Quick review one day before, and that will be it, okay? Like, make sure you understand you know how to do those skills on the lab reports. I think the lab reports are more valuable than the midterm, okay? Any other question concerning midterm? Now, any questions concerning lab 4? Shall we go back to lab 4?
Doctor, the midterm is this Saturday?
The midterm is on Monday, isn't it? How come you're asking me, Imad? This would freak me out.
دكتور مش عارف انا.
ايه بس ليه منك عارف شو السبب؟ يعني اكيد انا عملت شيء غلط معك. announcement ما وصل لك؟
لا دكتور ما خاص يمكن انا ماني قاري الميل او شيء
Alright, مش مشكل. Dear all, this is to confirm that the midterm for Physics 302 is going to take place on Monday at 7 chapters to be covered. أنا عملت غلطة واحدة. I should have written we will be using responders, therefore you cannot use Excel. Probably I can edit. I will edit. لأنه for other classes I did, because I know some students probably can miss some news, so I cannot blame you, Imad. So, and this was posted on Thursday, last Thursday. Okay, so yeah, I freak out because I want everybody to know everything. All right, so Andrew, you need a summary for lab 4. Is that what you mean? All right.
Yeah, you were saying we can go back to lab 4, so I would love that, please.
Okay, so I wanted to answer your questions, but if you want us to go quickly, why not? The manual is open just for you to see what to expect, right? You don't want to be surprised this evening. I totally understand. Let me throw myself on the table of contents because this document is not very friendly and we're planning to change it soon. All right, so what to expect? You have a question to answer concerning the egg drop contest, the impulse momentum theorem, how time of the collision and the force applied actually are related, and safety a bit. This is prior to discussing your results. Then you are given the collision. You need to understand that the cart is colliding with the force sensor. The force sensor is not moving. The force sensor will give you the area under an FT graph, that's the impulse. The motion sensor will give you a VT graph, so you can find V before, V after. Everything else is calculation, so all that is calculated. Okay, how do you calculate P? It's M times V. Delta P is final minus initial, and the difference, you actually do the difference between the delta P, which is here, and the impulse, which is here. Okay, both are experimental. This one is measured by the force sensor, and this one is measured by the motion sensor. So both are experimental. How do you find the percentage difference? You pick a reference of your choice, you do the difference divided by the reference times 100. Then you answer some questions related to why do you want to keep a constant angle? Basically because we don't want a lot of variables. They're discussing a bit the angle with the whatever measurements you're doing. Then they want you to compare the impulse to collisions, abrupt and cushioned, and they want you to discuss airbags using your results, list the sources of errors, and some conceptual questions at the end. Now, concerning sources of errors, I can see some weaknesses, and probably I can include this in my feedback before the midterm. But why not discussing it right now as well? Sources of errors. Errors are not mistakes. Errors exist on your setup. You know they are there. You try to reduce them, but you cannot get rid of them. Exactly like friction. You know friction is there. It's not your mistake. It's not the partner's mistake. It's not a calculation mistake. It's something in your setup. You reduce it. You try to pick the best procedure possible, the best track, smooth, to reduce your friction. Probably you try to pick a mass and an angle that would give you the ideal case, but you know for a fact that you cannot get rid of it. This is an error. Your measuring tools, they have limited precision. You pick the best scale possible, that is usually the smallest scale possible, or in other words, the more decimals possible, but you cannot have an infinitely precise measuring tool. It has a limited precision. Sometimes human error is there, and trust me, in most of the experiment, the human error is not there. It's only when you need to time something. The reaction time of a human body is slow. When you decide to stop and start the watch, your finger needs time, you know, to react to the stopping and starting signal of your brain. This is a human error. What else? You can discuss sometimes some tiny things in your setup where, for example, we assume things to be horizontal, however, the desk is not. Sometimes you assume gravity to be 9.81 in the lab, and probably it's not, you know, some assumptions. So these are errors. Rounding is not an error. Calculation mistake is not an error. And please don't tell me we have error here, 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 and there. The question is, why do we have error? Because of the limited precision of the measuring tool. Don't tell me I have an error on the mass. Due to what? So try to say due to what, okay? I know that you still have, probably you need time to know what I mean, and it's okay. Just to try to elaborate more on the errors you list in the lab report, and ask me if you need to, okay? If I send you a list of sources of errors, probably you can pick from this list. Any other questions related to lab 4? Uncertainties required for this lab. Let me see. Apparently they don't ask for any, so please don't write it unless you want to for a certain reason, probably to round or something. Okay, I know that all the measurements are digital, or the measuring tools are digital, the mass, the impulse, which is the area under the curve, v before, v after. So it will be easy for you to write down your uncertainties if you need to. Okay, so I don't see a requirement. And again, the requirement I'm talking about is the minimum requirement, and that's a template, and you can do anything more if you believe it will help you in any of your questions. Any other question? So please stop me if you want me to go back to lab 4. Now I need to start with lab 6. Lab 6, the physics is easy. The physics related to the setup is a bit confusing though. However, it will not affect your data analysis and your data analysis. So I will try to go through the equations and to tell you where to derive the final product. However, you just need to use the final product. Before we start, you need to know the minimum understanding of how rotational motion is, and I really care about inertia, okay, in specific. The outline is gonna be rotation versus translation. I know that you have an excellent understanding of translation, so probably try to create a chart on how I can see different items on rotation. For example, for linear velocity, I have angular velocity, and for force, I have the torque. And what I care about is mass and inertia. Inertia for rotation and mass for translation, for you to understand exactly what inertia is. I forgot to include a very important idea that probably I can explain orally. Then I need to start by defining rotational inertia for a point system, something that probably you know from high school, and I need to extrapolate to any system, not a point system. I will start showing you the setup quickly, discussing the acceleration of my setup, show you the experiment in a video. This experiment was recorded last week by me. I didn't have the chance to watch it yet, but hopefully it's good. And eventually the lab report what they want and what you need to measure and calculate. Okay? Yes? All good? All right. What you need to know, rotation versus translation. I love this. I love this table. So every time you need to discuss, let me zoom in. That's why all my pictures are on the left. So every time you need to discuss position and translation, position on the x-axis, now we need to discuss angular position like an angle in rad. Every time we need to discuss the x component of the velocity, we're gonna discuss now the angular velocity in rad per second, that a lot of people call angular frequency. Acceleration meter per second squared is gonna be alpha, which is rad per second squared. The force, Newton, is gonna be a torque, Newton dot meter. I don't know if you remember torque well. Did you do any torque in the course yet? All right, I totally understand. So I'm gonna start reminding you what torque is. The only attempt you had for torque was in grade 11, and probably it was not as rigid. So probably you're not as good. You just need to know the definition though. Sigma force equals ma. This is the best way to tackle kinematics versus dynamics, Newton's second law. How do I do it for rotation? Instead of doing sigma f, I'm gonna add all the torque. However, there's a mistake or something I don't agree with. Torque is a scalar and not a vector. So by adding the torques, however, the torque can be positive and negative if the rotation is clockwise or counterclockwise. Same thing for alpha, which is the angular acceleration. So instead of saying mass times acceleration, I will say moment of inertia versus the angular acceleration. Forget about momentum. I don't need to, this is linear momentum, this is angular momentum. You can think about it, m times v, I times w. I is the moment of inertia, w is the angular speed. There's also kinetic energy, one for translation, one for rotation. Isn't that wonderful? So half mv squared, it's gonna be half I w squared. And so on, like everything, all the laws in translation, you have the same for rotation written differently. This is another chart because I simply love this chart. Position, angular position, displacement, by the way, this is delta x, I will have delta theta, velocity, angular velocity, acceleration, mass and inertia. By the way, you know inertia, mass is inertia for translation, I is inertia for rotation. I don't know if you know the famous dancer rotating on the ice skating arena, and by simply closing his arms and reducing his moment of inertia, he can go faster. And by opening his arms, like increasing the moment of inertia, he would go slower, like increasing inertia and heaviness to the rotation. You know for a fact that the heavier you are, the more you resist the motion, translation. In rotation, the bigger the I, the moment of inertia, the slower the rotation would be, okay? Anyway, so mass is inertia for translation and I is inertia for rotation. And this is the objective of the lab. 2, rotational inertia of a point system. How do you find the moment of inertia, or you can simply call it inertia, for a point-like system? You take the mass and R is how far away it is from the center of rotation. For example, this is a point-like system. You do M2 times R2 squared. Don't forget to square. What is R2? It's the distance, let me call it simply distance between the point and the center of rotation. The center of rotation could be anywhere. For a rod, for instance, let me show you a rod. You can rotate the rod from here, and rotation is gonna happen like this. Or you can simply rotate the rod around the center and rotation is gonna happen like this, right? So the center of rotation changes everything. You need to know where the center of rotation is for you to know the distance from the center of rotation. And now probably I can ask Andrew. Andrew, you freak me out every time you send me a message on WhatsApp because of your nickname and your angry face.
Don't worry.
Because I assume you're angry, you know? And angry means
No,
I
don't
need
do
to
it.
be
Doesn't
careful how to
signify
talk
anger.
to you. Yeah?
Yeah, it's okay. It's okay.
Yeah. Are you angry right now?
I'm not. I'm very happy.
Okay. You can be angry and happy, you know?
Depends on the mood.
Yeah.
And
And why the anger in your nickname?
It doesn't signify anger, doctor. It signifies dedication. And if you want something and you want it bad, so you're willing to work hard for it.
Ah, it's good to know. So it means serious in a way. You're too serious.
Yes, exactly.
Okay. Which means you need
Maybe,
an answer and an answer now. So I leave everything to answer you.
It's not good to send it to a doctor, but somebody else.
Yeah, you know, when you send me a message, I freak out, I throw the phone, and then breathe, and then all right. Anyway, Andrew, yes. Okay, Muham, what is the unit for I? That was my question.
Mass grams, radius meters.
شو grams يا مان؟ شو grams؟ خربطت الدنيا. شو mass grams؟ Okay, so SI unit.
What is M in this case?
Okay, SI unit for mass is kilogram. Okay?
Yeah.
Okay. What about the distance? Or R or anything?
Meter square.
Okay, meter square.
So kilogram, meter square.
Exactly. So inertia for rotation is kilogram. Inertia for inertia for translation is kilogram. Inertia for rotation is kilogram dot meter squared. And this is something that we need to think about. This object seems a bit farther from the center of rotation. I know nothing about the mass. This is simply another example. So you can use this in case you have a point-like system. In our case, we don't have a point-like system. If you read the title, you have a disk, a flat disk that is actually heavy, and you have a ring, like a big bracelet that is thick. I will show you a lot of pictures and videos in a moment. So I cannot use this equation to find the moment of inertia of my system. However, I will use this one and do the integral over the whole disk. Definitely, you're not going to do the integral yourself. Before discussing the integral, if I need to take, like this is a point-like system, I do mr squared. If I have many masses, I can do m1 r1 squared plus m2. Like I can simply add I1, I2, I3, which means if I have, and let me see if I can scroll through this one, probably throw the chat away. If I have a rod, a full rod, the best way to find the moment of inertia, take a tiny part and then do the integral. So it's tiny m times r squared. Tiny m can be written in terms of tiny delta L, and then do the integral from this side to this side, or probably no, from this side to this side, times 2. Anyway, I'm trying to tell you how we find the moment of inertia of a system which is not a point-like system. This is how we proceed. In your case, you simply need to know that you can find online the moment of inertia of anything you want. Of a solid sphere, this is the solid sphere. This is a hoop. Okay, what's the difference between this hoop and this eye? This is when the center of rotation goes around the center, and this is where it goes around the diameter. So it makes a difference. The rod, the center of rotation is around the center, and this is on the edge. So it actually is a bit different. Okay, and this is a solid cylinder. This is another table that you can find online with a lot of details. It shows you a solid sphere, a hollow sphere, a rectangular box, the rod, the famous rod. In our case, we need something like this one because we have a ring that looks like a cylinder, hollow from the inside. So as you can see, it's half mr1 squared plus r2 squared. R1 is the outer diameter, R2 is the inner diameter, and yes, we're gonna measure this. We also have a disc, and a thick disc. It could be something like this one, okay? This is a circular plate, a plate like the plate, spaghetti plate, and it's gonna rotate around the center in both cases. I will show you in a moment, okay? This is our setup. This is the disc I'm talking about, okay? It's thick, and rotation is happening around the center. And this is the ring, it's hollow from the inside. So yes, you can find the diameter, the inner and the outer diameter. All that is nothing but the rotating platform, okay? What is it? It's basically a stand, and on top of which you have, you can call it a pulley. It's simply a disc. And this is a wire. By the way, the wire is very important because you're gonna rotate the wire around the pulley. And you have a heavy hanging mass. When you release the mass is gonna pull the wire down. The wire is gonna pull the pulley, create a torque to rotate your system. I tried on the video with a very small mass, probably 20 grams. It was not too heavy and the system did not rotate. So I had to increase the mass. I just want you to feel how heavy the system is. However, you have to be careful because you have 3 step pulleys. Yes, they are called step pulleys. It's very important to know the name. I will tell you later. So step pulley. What is a step pulley? A step pulley is basically a wheel, and you have 1, 2, 3, the diameter of which is different. I think in the video I picked the bigger diameter because I want a bigger torque. I will explain the torque in a moment. So I rotated the wire around the bigger step pulley. I took the measurement of the diameter of the step pulley using a vernier caliper just because it's easier to handle and to tuck it in to be able to find the diameter, because a regular ruler won't help. And then I released my system. The system will create a tension in the wire. The tension is the force. The force gonna pull on the pulley and rotation will happen, okay? So, and my purpose is to measure the acceleration of my system. However, I forgot to explain how to use the photogate in here. Photogate. What is a photogate? We have a photogate, and I will show you in the video as well, attached to my smart pulley. The photogate is a new sensor that is similar to the motion sensor, but it functions a bit differently. It can tell me how fast the pulley is moving. So this definitely you will end up with a VT graph. We like the step pulley because usually the step pulley is used whenever you have openings. Like you see the wheels of the pulley, it's open, closed, open, closed, open, closed. It tells the photogate the photogate will measure the time through the opening, and then the time through the closing, and the time through the opening, the time through the closing. It's very precise. It's used in such cases when I cannot use a motion sensor. Okay, I will show you on the video how it works because I want you to understand how it works. Very user-friendly, doesn't need calibration, nothing. You just need to tell the setup, and usually it says in the setup how thick those black lines are. You see the thickness of them. All right, this is a different picture of your setup. Yes, you can see again the pulley. This is a smart pulley with a photogate. You see the 3-step pulleys here, the disc, the ring, 3-stage spool. So yes, we're gonna use one of these. I will give you the diameter of these. In our case, the smart pulley was not clamped on the table. It was clamped on the stand, but it's no difference. And this is the heavy weight to actually pull the wire and create some rotations, okay? All right, now let me try to explain a bit, yes, what you need to understand. First, the moment of inertia of the ring, we already used the table to know that is half So M is the mass of the ring, R1 is the radius of the inner radius, and this is the outer radius. This one is for the disk of uniform density, which is not perfectly the case. It is uniform in density, but it has a slot to put the ring on. So it could be a tiny source of error. You can easily measure the radius of it and the mass of it, and both will be given to you. Now I need to remind you that F equals ma, right? That's for translation. For rotation, instead of force, I'm gonna use torque. Instead of M, I'm gonna use I, the moment of inertia. Instead of A, I'm gonna use angular acceleration, okay? Now we need to define torque. If you go back to grade 11, torque is simply the force cross R. And this is force as a vector and R as a vector. I will explain R in a bit, and this is the cross product. I know that probably you hate cross products because probably you're not in love with math. So I'm gonna change it into F times R times sine theta, and theta is the angle between R and F. Very simple. Let me show you a disk. I need a reasonable color. Okay, this is viewed from above. And this is the force on my system. Let me make it a bit bigger. Okay, this is the force. So imagine I'm pulling on a disk. And this is how far it is from the center of rotation. So this is R. So R is the distance between the leg of the force and the center of rotation. In this case, you can see, hello, John, you can see that the angle here is actually 90 degrees, and sine 90 is gonna give you 1. So in our case, we're not gonna use sine. You don't need to worry about it. It's only when the force applied is not perpendicular to this is usually called the lever arm, okay? So torque is the force applied over a certain R. I would want to discuss a bit the door because this is something you use in your daily life. You know the door, you see the door behind you, the door of my kitchen, or you can call it my office, because nowadays my kitchen is my office. So this is the door viewed from above. And this is where the door is fixed. So this is the fixing point, or you can call it simply the center of rotation. I can push the door from the edge, or I can push it from a length, quarter of the length, or from the center. This is push 1, this is push 2, and this is push 3. I can ask Yara, in which case you can create more motion if you push at the edge or at the center, in case 1, 2, or 3, Yara. At the edge, exactly, because for rotation, I don't care about the force only. I care about the torque. And the torque is greater when R, the distance away from the center of rotation, is greater. Okay? You know, if a kid would come and push the door very close to the center of rotation, you can create probably no motion. And if you push at the center of rotation, even if the force is doubled and tripled, rotation will not happen, you see? By the way, the unit for torque is Newton.meter, okay? So for rotation, the force is not enough to measure. We need the torque, which is force multiplied by how far away you are from the center of rotation. So this is written as torque is R. By the way, R is the radius of the step pulley because the wire is gonna pull on the step pulley. I'm gonna show you in a moment. So if you want, you can call this the step pulley, which is under the disc. And this is the tension in the wire. And R is the radius of the step pulley. So T means tension in the wire. You can call it force, okay? Now for the next slide, I'm back to this. Torque is R times the force. How can I find the tension? If I do net force equals MA, probably discuss a bit here, and I can ask Eli to help me. Eli, what are the forces on my system? So this is my system.
I can't read the system exactly.
Yeah, what's the forces on my system?
The one hanging?
Yeah, very easy.
Oh yeah, the tension in the cable and the gravitation, the weight,
yeah. So tension T and the weight mg. Okay, is the object at equilibrium?
It is.
If I release it, it's gonna move and rotate the disk. So it's not at equilibrium. So I'm gonna say net force equals ma, sigma f equals ma, and I have an actual acceleration. The acceleration is downward though, okay? So downward means mg is along the acceleration, t is opposite to it. So I'm gonna write mg minus tension is equal to ma and not t minus mg. Now, how do you find the tension? Can you help a bit? Simple math.
MA minus mg.
Okay, so the tension is mg minus ma, right? Mg minus ma.
Right. Yeah.
Okay, so you're gonna say m into g minus a, and this is what we just get here. Okay, so in the lab report, they used up to be the positive direction. So they had negative for a and negative for mg. In my case, I simply did that. I always take positive direction to be the acceleration to have less minuses, but whatever you do, you get the tension. All right, so now we have many equations. The torque is R times tension. Okay, so the torque is R times tension. So Yara, which part you don't like? Now that you infested the chats, I cannot ignore you anymore. So you hate torque, right? Or is it rotation that is confusing for you? The color of my pen, what is it? Okay, you're eating. All right, anyway, you can write anything in the chat, it's okay. So back to here, I'm trying to mix all the equations to come up with this. So this is my target. Okay, so what I need to find the moment of inertia of the system, any system I would put on my platform. To find the moment of inertia of any system, I need to do torque over angular acceleration. Why is that? Because we already said that torque is I times alpha, which means I is torque over angular acceleration. So I want to use this. So I need to find the equation for torque, the equation for alpha, plug them in this equation to end up with a big equation and measure a tiny little thing, okay? So don't freak out. If you don't understand this, you will live. But if you do understand it, you will enjoy the lab more. So instead of torque, I'm gonna use R times tension, and the tension is this. Remember, R is the radius of the step pulley, because a lot of students would think R is the radius of the disk. Now the angular acceleration is the linear acceleration times the radius. Do you remember from Mawarif grade 11 that the angular speed is speed over radius? And the actual angle is the actual displacement over radius. And the angular acceleration is the regular acceleration over radius. Okay, you know for a fact that the length is 2 pi r. So angle times r, yes?
No, بس عامل لك انه that's what we're learning in physics right now بقى كله بعرفه.
Yeah. So basically, if you want to move from rad to meter, you multiply by the radius. So rad per second to meter per second, you multiply by the radius. Rad per second squared to meter per second squared, but it has to be the tangential acceleration. And this is what we're going to measure, not the centripetal. You simply need to multiply by the radius. Okay, so now I have I to be torque over alpha. The torque is this equation times tiny r, and alpha is this equation, like A over R, and you plug them in. You do torque is this, alpha is this, and this is not a plus, it's a divided. I typed this equation, my bad, it's a typo mistake. Dividing by this ratio is like multiplying by the opposite, and you expand and you get this. What's M again? M is the mass of the hanging mass. So this is small m. Be careful because you're going to be confused between mass of the hanging mass of the disk, mass of the ring. What is R? R is the radius of the step pulley. It's here. G is gravity, NAMPO 81. And yes, that's an assumption. AT is the only thing I need to measure, the acceleration. The step pulley is, the smart pulley is going to give me the VT graph anyway. Slope is the acceleration. So for you to find I, we don't have a measuring tool to measure I. You know the mass, you step on a bathroom scale, you measure the mass. How do you measure I? You cannot. You can calculate it, or you can simply measure the acceleration, how slow the increase in speed is going to be to discover how lazy your disk is and therefore how big the inertia is, okay? So the experiment is very easy. Understanding how the acceleration affects I, it's a bit complex, and no, you're not responsible to know the derivations, okay? However, it's good to understand a bit how things are. Do you have any question? Did you miss any step? It's okay, even if you don't need to know this, it's good to ask because it helps you understand what's happening. Go ahead, which step did you miss? I tried to display the equations clearly. Did you get it? Any question? All right, if you have no questions, I can wrap up. Basically, this is something I'm showing you the last slide, and I will get back to it in a moment. So this is a VT graph, just for you to know what to expect. This is V versus time. But when you release the object, you will see in the hanging mass is gonna free fall, but it's not really free falling because it's gonna pull the disk with it, and the disk is big in size and heavy, so it's lazy, so it's not gonna accelerate the way it does when it's free. So you see the speed 0 speeding up very slowly, and you will see it in the video, and then it's gonna hit the floor. Ignore the hitting the floor or the end of the wire. And as you can see, I have this yellow selection to find the slope only for the selected part. And you can read on the Data Studio the slope of the line, which is the acceleration. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 trials, ring and disk together, disk alone, to find the acceleration. You're gonna find the average and the RMS. By the way, the trial takes 1 second. You just release and repeat, release and repeat. The software does the measurements for you. We believe the motion is very slow and probably there's a lot of friction. That's why we do a lot of trials. And especially that the experiment is quick, why not do 10 trials? By the way, when you find, so back to our long equation, by simply knowing AT, you can tell I of your system. If you know, back to here, if you know I of your disk and you know I of the ring, how do you deduce, like, let me say it again. And the question is for somebody that I will pick in a moment. If you know the I of the disk and the I of the ring and disk together, how do you find the I of the ring? And the question is for Karen. Do we have a Karen or Karine? Probably. If we don't have a Karen, probably we have a Priscilla.
Hi doctor.
Hello Priscilla, how are you today?
Good. في كارن يعني بس معلش. مش قصدي أنا وكارن.
She's quiet.
Anyways, doctor, I have given the eye of the disc, and then I know the eye of both discs.
كيف تنسم بريسيلا معصبت ايه؟ ليك كارن
لا
كارن is saying I'm sorry.
عم بدافع عن صديقتي الأم لنوقعها. كارن وينك كارن.
Alright, مالي هلا بدبر لها سؤال لكارن يكون هيك تقيل شوي. Okay, so back to you, Priscilla. Yes, if you find I of the disk and you find I of the system ring and disk, how do you find the I of the ring alone?
I system ring and disk minus I disk.
Yes, exactly. So I is very simple because you can add I of many objects together when you have a disk, a system. Like if you have a system made of 2 items, you do I1 plus I2. So the problem is I cannot put the ring alone on the platform. If you look at the platform, you cannot put the ring, it's empty from the inside. That's why I'm obliged to do the experiment with disk and ring together and minus the disk later on. I just want to make sure you guys understood this one. Now let me show you some screenshots of the video, and then the video. I hope the video is clear. This is the platform. This is the disk. You see the tiny hole special for the ring, you know, so I put the ring on top, and this is the like a stand. This is the photogate, and this is the pulley inside, and there's a wire. Here I'm trying to attach the wire around the biggest diameter step pulley. I was rotating it, and then around the pulley down, this is the hanging mass. In the video it will be more visible, and this is a screenshot from the video to show you how you expect your results to be. Okay, I would want to save this, otherwise I will forget. All right, so before I go back to the lab report, let me show you the videos. Which one comes first? This one, I think. Okay. And again, those videos were taken using Ms. Jinan's phone and not my phone. So again, what we have, hopefully the thing is nice and clear. This is the step pulley, you see it? You have step pulley 1, step pulley 2, step pulley 3. This platform is nothing, probably to attach the wire on, like to create a node, okay? And I'm gonna put the disc on top of all this. This is the disc, it's heavy. Okay, it's big, it's really heavy, the mass of which will be given to you. I will make sure to put it, there's a slot here specially for it. And I'm showing you the rotation, how fast they are. And you see, as I'm rotating, the wire is moving up and down. You see the pulley, the hanging mass. This weight is very light, and it's rotating around the step pulley. Okay, now my job is to remove the disc again. I'm showing you how I put the ring on top of the disc, and this is gonna happen later, explaining that this is my system, and I'm gonna measure the diameter, the masses, and remove the disc. All right, now I'll take some time to show you the wire. I know that the wire is not very visible, but you can see that I have a wire in my hand. This is the hanging mass. All right, I will put the wire on top of the pulley. I'm explaining what is the photogate. I asked Ms. Jinan here to show you probably, you see the wire, you have 3 step pulleys. I will rotate the wire around the biggest one because I want the biggest tiny R to create the biggest torque. And I want to make sure that the angle between the radius and the wire is 90 degrees, because why assume 90 if imagine the smart pulley is just at a certain angle. I made sure that the wire and the pulley are aligned, which means 90 degrees. And this is a big source of error. A lot of students used to ignore this fact. Okay, so yes, taking my time to create the rotation and to explain. Okay. Where's the part where Ms. Jinan was showing you? That's it for the video. Okay, now the next one. Yes, I want to show you the photogate and how it functions, because I found it difficult to explain. So the photogate has 2 terminals. It sends an infrared radiation, okay? Exactly like the remote control of your TV. And it's gonna go through the wheel, and the wheel, you know, it has black slots and empty slots. So it's gonna be interrupted intermittently, like empty, closed, empty, closed, empty, closed, and it can be fast, it can be slow. So the photogate can measure how fast the wheel is going by simply measuring the time through which it's being blocked, okay? So, and you have a signal. So I'm explaining here that there is a signal going out from here received by another receiver. And Ms. Jinan will show you with her phone a tiny light that will go on every time I block the signal. On, off, on, off, on, off. So this, I can use this through the smart pulley. Every time the pulley is rotating, it can measure the time through which the beam has been blocked, knowing the sizes. So I really wanted you to understand how the smart pulley, or the pulley with the photogate, pulley plus photogate, will be called smart pulley, functions, because probably this is your only experiment in which you were gonna use a photogate, you see? So it can tell you how fast the wheel is going, and definitely the software knows how big the wheel is, and therefore it can do the measurements. All right, so here I do one experiment. 1 second, the experiment was done. Show me. And the speed. So the time through, if the time is very short, it means that the pulley is going faster, right? So okay, how come I got this graph? Probably this function of time. And this is the first part before the thing has stopped. So I only took... Usually the wire ends and the hanging mass will do the oscillating motion at the end. That's why I have this weird something to ignore. Sometimes if the wire is too long, and it happened on many benches, it will simply hit the floor. And this will show me the end of the process. So make sure you select only the linear part. And it's a beautiful line showing you it's a constant acceleration. Okay. Yes, probably I'm gonna do the experiment in front of you. I'm rotating the wire. I will click record. I will release, and you will see the line happening. Okay, so, and you see that the line is basically flat. Flat means the acceleration is so small because the disc is so heavy and the motion is so slow. So you see how small the slope is? Here I had to zoom in to show you the thing. Okay, and here I'm repeating probably. I don't know what I'm doing. You can watch the video. All right, so this is another attempt. So make sure to select only the linear part and ignore later on. So this is selection, only the linear part. The slope is probably visible. Let me see if the slope is visible for us to see.
The moment of inertia of your disk. You are also required to find the moment of inertia of the ring. However, the ring cannot...
No, the resolution of the video is not great. So I think it was 0.02. It's that small. I just want you to have an idea. Like free fall 9.81. This is 0 point something, you see? Just for you to see how slow it is. Now I will add the ring and I will repeat 10 trials and see how things would be. That's it. So experiment is very simple. The only difficulty students usually have is to make sure the pulley, the smart pulley, is aligned, and to know how to take the measurement of the radius of the disc, the radius of the ring, inner and outer, radius of the step pulley. It was confusing for them, you know. If you misunderstand which radius we're talking about, you will have weird results at the end because simply you did a mistake and you picked the wrong mass or the wrong radius. However, by simply releasing your system, you just need to take the slope. Doing it 10 times will take you 10 seconds, repeating with the ring, and that's it. All right, now I can show you what you need to measure, and I can see that people are frustrated. They love the experiments. Priscilla just wants us to be together. Yara wants to go on campus. I know you're frustrated. I totally feel you. I'm equally frustrated. Today I went to LAU. I was there for only 1 hour and 15 minutes. But I drove for 50 minutes times 2, and I think it's worth it. I think it's worth it. I wish I can go every Monday. I recorded 3 experiments for your class, actually. It was nice, you know, because lab without the experiments will lose the purpose. And personally, I enjoy the experiments more than teaching the experiments. I enjoy the benches, you know, and I enjoy seeing how the mistakes you do on the bench, and I enjoy to waiting for you to figure out what you did wrong. But giving you results and giving you presentations, this I enjoy a bit less, you know. So personally, as a physics instructor since 2006, that was my passion, and I am not doing any of what I like. So I totally feel you, okay? But I have a feeling that things is gonna end soon. Don't you see some light at the end of the tunnel? Because personally, I see a lot of light. I hope so with the vaccine. I don't know. You should tell me. You know more about that. Now I see a long tunnel. I'm not talking about all the tunnels, Ellie. I'm just talking about COVID, okay? I know there are many tunnels out there. Let's focus on COVID for the moment. So the lab report, what to expect. Step pulley radius, the one I used, will be given to you. Ring inside and outside diameter, inner and outer. Mass of the ring and mass of the disc and the hanging mass. All this should be given. So all this you're supposed to measure in the lab. So it should be given to you. Analog or digital, it will also be given to you. Now theoretical values. To find I disc and I ring, by the way, you know here that I of the ring is given. This is the theoretical equation for the disc. You just need to do the theoretical calculation. Now plus or minus means you need all the uncertainties and you need propagation of error. Not a big deal because you just need to do it once. Now I will fill in this for you, You will calculate the average, the RMS, deduce I for the ring and for the disc. Okay, and there's a table that is not visible on my slides, which is a summary of where to put all your theoretical values for I, the experimental values for I, and then you're gonna do the percentage difference and discuss sources of errors and discuss many questions. Okay, so I don't see you have a plot, and I don't see it a bit long. I was a bit worried about you understanding where I got this equation from. I need you to understand where I got it from. I don't want you to be able to derive it alone, but you need to understand why I is related to the acceleration. If you don't want to do the math, just think about it. The bigger the disk and the heavier it is, the lazier and the slower it's gonna be. So by simply putting a big hanging mass, the hanging mass is gonna pull and pull and pull. It's gonna speed up, yes, but the acceleration of the hanging mass will depend on the moment of inertia of my disk that is rotating. You see what I mean? So the more spread the mass around the center, like farther from the center, the lazier it's gonna be. Just imagine your big sister lazy, sleeping, and you need to drag her out of the bed to take her to shower. Huh? Yara inside. She's 10 years old. I do this every day. Drag Yara to the shower. By dragging, I mean her character, how lazy she is, you know? And this is inertia for translation or inertia for rotation. I'm not talking about you, Yara. I'm talking about my daughter. And you're very dear to me, as dear my daughter is. Yes. Yes, probably you're much better and you don't need people to drag you. You're full of energy, I know, and I hope so. So this equation is very important to understand for you to understand your system, okay? So, and that's it. I'm done for today. I'm done for lab 6 actually. If you have any questions concerning, by the way, the deadline to finish lab 6 will be a bit pushed away for you. I'm gonna give you a few extra days, but not a lot. Yes, we're meeting next week regular at 2:30, even though we have a midterm at 7. I don't see why we should skip one session. I don't want you to end up overwhelmed over at the end of the semester. Let's not skip because we have Easter Monday anyway. And yes, probably I will give an announcement because people would say probably we're gonna skip. Let's not skip. And probably you will be happy to see me before the midterm because you will have some questions. I'm sure you're gonna need us to meet anyway. Okay. Now I was discussing the deadline to present lab 6. I want to push it for a few days, but not a lot because we're gonna do lab 8 afterwards. I don't want all the labs to be, you know, on top of each other. And I don't see the labs, those coming labs being long. They're not actually long. I think in an hour or two max, you can finish the lab report. And if you are two working on one lab report, it's gonna take you so much less, you see? So I think it's okay. At least you finish from the lab reports. Now the big deal is who is gonna correct them. I'm too slow and that's the problem, but you finishing from the lab reports, that's step number 1 done. And don't worry about me correcting them. I will find a way. Okay? Any other questions? I will stop recording, but I'm staying here for any question you have.